Welcome back to Scripting with Gavin. Today is a little different video. I'm gonna show something I've already coded, and there's a bit, but basically I like generating terrain, and to do that a cool way is using perlin noise. So I have two scripts. This one is the main one, I think. It generates a grid of points given these inputs, and we can use that to make a pretty cool map. So let me, explain this stuff. So there are these arguments. The length is just the length of each side of the map we're generating, and it's a square because why not? The resolution, it's how similar neighboring points are to each other, and I like summarize this as sameness. And oh yeah, I should probably explain what perlin noise is. It's like you could generate a grid of points with random values, and that would like be noise. But perlin noise is more good looking because it's like points that are near each other are like similar. Like it's still random, but not like completely random because uh, of the similarity between points. But it allows for cool things like making terrain and uh, waves for water and stuff, or like it looks more natural. So yeah, and this is the script that just makes the grid with the values in it. But yeah, the resolution is how similar the points are to each other. The frequency is it's like how often peaks and valleys will appear, and I call this waviness. And the amplitude is how basically how strong it is. So like if I set the amplitude to like 10 instead of 5, it would look like this. You see how like it's taller? It's not like uh, crazy. It's not like directly related to the actual noise generation. It's just how it looks visually. So, yeah, those are the arguments for this way to generate noise. And I got this from some video. It was like a roblox perlin noise tutorial, and I like made the code based on that. So this is just making like a roblox class, you know. I'm gonna go through the code really quick. So we have a function that gets the height. Well, I'll skip that right now. First, let's go to the loop. So we just need two loops. Whoops. For each axis of the noise map. So there's two. So you have x and z. And at each at each point we need to get the perlin noise value, and we're just making a part here to visualize it, but this is the real thing to look at, is the get height. So it basically does the math.noise function, which takes in 3 arguments, x, y, and the seed. And it's not like, it's basically, it doesn't have to be y, it can be z too, but basically 2 arguments to indicate position, and then the third one is the seed of the noise. So we still need to do a few more things. We can't just put the point directly. For some reason, I know there's an explanation for this, but I forgot it. But basically, the noise function returns 0, I think, if the one of, I think it's one or both of the position arguments are integers. So you have to make them not integers. So to do that, we divide it by the resolution, and to uh, get like the waviness, you also need to multiply it by frequency, and that like well, so basically the resolution, it's zooming it, like if, okay, how should I explain this? So basically this is a noise map, but the resolution, you can change it to like zoom in or out. So I can set it to 50 to zoom out, and now you can see there's more stuff, but we can keep like the higher the number, the more zoomed in it is. So oops, not 10. 10 is really zoomed out, so there's like a bunch of hills and stuff, but the frequency, it basically reduces the amount you zoom in, which means it zooms out, so then you have more hills. That's probably a terrible explanation, but anyways, now we have the height is what we call it, the noise value, and we need to clamp it in between, well, what it's supposed to do is return a value that's usually in between negative 0.5 and 0.5, but it doesn't always do that. So to keep it in that range, and we actually want to make the range 0 to 1, we're going to clamp it in this range and then add 0.5. So if it were like negative 0.6, it would be clamped to negative 0.5, and you add 0.5 to get 0, and that's the lowest value, and same for the highest, so it's 0 to 1. And we want 0 to 1 here because then we can easily set the color of the part to visualize it, because 0 is black and 1 is white for normal color 3, so that's what it gives. and we put it in a table, or I wouldn't, I forgot to change this, but I would not index the points table with a vector like vector2.new, because you can't like find, you can't access it later. I realized that in making another uh, noise script, but yeah, I made this function that I used at one point. I don't think I use it anymore, but it just goes through the points and see which one's the highest. And this one just destroys everything. But yeah, that's like the most basic form of perlin noise here. And just chill. Oh, that's a lot of parts. But we can do better. So let's do that. Here we go to noisy 2. And this one is based on a different video, a perlin noise video. It's not Roblox. It's Sebastian Lags, like, I don't know if I said that right, but it's his terrain like generation series. I learned it from this, but we have um, the module with the class in it, and basically there's more and different sort of variables or arguments now. So we have the x and y, which is just the size, the noise scale, which was the resolution, and I thought it was fine to have it set at like 25% of one of the dimensions. And there's new stuff. There's octaves, which is, okay, so basically what we've added now is fractal noise control, and basically, or fractal noise, basically what that is instead of generating one uh, grid of perlin noise, we generate multiple and add them together. So each octave is a different grid, and so right now uh, our map is made up of 7 different uh, noise maps that are merged together. And we have a new variable, persistence, and basically it's how much influence the next octave has on the map. So basically what that means is, let's say we have our first octave, and that's like the base of what the map should look like. Then the next octave should just add detail to that base map. So to not like completely overload it, we have to uh, make it have less of an effect on the overall map. And that's where persistence comes in. And persistence, basically, it, let's see, it reduces the amplitude by whatever it is every octave. So the amplitude starts at 1, and second octave it'll be 0.5, third octave 0.25, fourth octave 0.125, and so on. Then we have lacunarity, which is a cool word. It's basically affects how detailed the next noise map used will be. So the first noise map, the first octave, well, that's used as a base, it's not very detailed. And we use linearity to increase the detail or frequency of the next octave by 2 times, and that like lets you have uh, little cool details, cooler details on the base map. And yeah, the seed doesn't matter, but the offset is like, it's just like one seed, you capture a portion of it by making a map, and the offset just affects what portion you capture. So like if uh, x was set to 1 here, it would move what amount we're capturing to by 1, but I can't really say the units because I don't know. it's it's weird. It's not like studs or anything, but it does affect what you're gonna see. I'm gonna show this first. It can load immediately, but I like to see it like generate like this. So you see, this is 7 octaves of detail, and it's like really like mountainy and stuff, you know? And I think that's super cool. And you can really see the difference if I like change it back to 1 octave. It'll be super smooth. Like, look at this. What the heck? That's crazy. And yeah. So let me just go over this. There's a few changes made here. First is we're actually storing it on a grid this time, not not vector keys or whatever. So I made the class just the table, and then in the loop where we make the noise map, every x we put a table in there, and then the y values are in that table. It's like it works. So, um, what is different? Let's see. We have an actual like random thing. So, uh, in this thing, we're just applying the offset we have as one of the arguments. Uh, we're applying that to the octaves, and it's random because it should be well, to make it look more unique, uh, we want the offset to be different from for every octave. So yeah, Sebastian, he like found this range, negative 10,000 to 10,000 is like where you can get like good detail, and anything past that apparently doesn't like do anything. I kind of forgot that part of the video, but it's whatever. And this is just a bunch of checks. You don't really need to include these if you know you're going to give it the right arguments, but uh, yeah, it's just making sure it doesn't like produce an error or something. And we have, oh, this is a good part. So in the last, the first version of the perlin noise, we clamped the values to 0 to in between negative 0.5 and 0.5, and then added 0.5 to get 0 to 1. But that can do something you might not like, where like you see this area, it's completely flat because it was clamped to negative 0.5, but it actually should go a little lower than that. It should make a nicer valley. So maybe you might not want that to happen, and I don't, because it's like it shouldn't be flat. So instead of clamping the values, we do this cool thing that Sebastian thought. Well, I thought it was really cool because I thought like you could do something like this, and then Sebastian did it, and I was like, man, he just like me. But yeah, basically what you do is you keep track of the minimum and maximum perlin noise values generated, and then you go through the grid and normalize each value based on those minimum and maximum. And you do this with an inverse lerp, which is linear interpolation. So basically, linear interpolation is if you have a beginning value and an end value, and t for the time, which is 0.1, so or 0 to 1. So if t was 0.5 and you had like the beginning and end values of 1 and 2, then it would return 1.5 because that's halfway in between those points. And inverse lerp, what it does is it gets the value you have and it returns t instead of the value. So it's like instead of getting x from a, b, and t, you get t from a, b, and x. Is how I explained it there. And that lets you have all these values in the range of 0 to 1. And then you can do your like color stuff with that. And yeah, the like actual generating the noise isn't very different. There's just another loop for the octaves, you know? And you don't need to like divide it by the octaves here because we're going to normalize it all in this step. So yeah. And yeah, and Sebastian, he didn't do the frequency and resolution in the noise thing. He did it well, he just made variables like this, but it's not really different, but except for this part, because when you adjust the scale or the resolution in the other one, uh, the other one, you know how resolution zooms in and out? We can, it zoomed on the corner because of how we used the points here. So to make it zoom in on the center of our section of the map that we generated, we need to subtract the x and y coordinates by half of the what's it called, the size of the map, and then we do divide by scale, times it by frequency, and then add the octave offsets here. And yeah, that's it for this one. And I took this and I made it a little cooler because I want to make a game where it generates a map, and uh, you like fight on this map, like make colonies and fight each other and stuff. But I wanted it to be completely surrounded in water. So first I'm going to comment out all this stuff because I want to show you what it looks like without the changes that I added. So all this stuff is normal. All I really did was change, well, there's a script for the noise map, which is literally the same thing. And then in this script here, I like uh, I give the points properties and stuff, like region uh, is just the color of the point, and it depends on the noise value at that point. So if it's from 0 to 0.3, it will be blue, 0.4, lighter blue, and all that. Like, so we get something cool like this. And it is huge because I wanted the values to whoa, wait, did I change this? Oh, okay, I made changes here that I didn't save. Oopsie, but I'll fix that later. It's not really anything big, it's just visual stuff, but uh, I it looks bigger here. It's the same size as the previous one, but I made the cell size 2 by 2 instead of 1 by 1 because I want it to look bigger, and it definitely does. And it actually looks pretty cool, like, wowee. Only problem though is even though it looks really cool, uh, it's only 500 by 500, so parts of the map will just be cut off, and that doesn't look good. I want it to be the map, and then the bounds of the map are just all ocean, you know? So what I did was I did a lot of weird crap here. I oops, did not want to. Okay, here, first thing I did was this code basically checks how far each point is from the center, and if it's like 70% of the map away, then it starts to apply a fall off, which basically lowers the point's height up to the deepest value, and well, which is water right now. It's not actually 0, but yeah. So the further you are away from the center, starting at 70% away, uh, the map will start like turning into ocean, and as this is really good. Only problem though is doesn't really work well with water because since everything is falling off in this radius, unless it was already water before, you can see the outline of the circle that it's like falling off in, and I don't want you to see that because that's like not, it doesn't look natural. And there's also these areas of like random crap because this was actual water and I made it like ignore water entirely because it's already water, you don't need to change it, but it doesn't matter for what I'm doing next. And this is the water fix. This is absolutely destructive on the first version I did. It took like minutes for the map to load because what it basically does is uh, it goes to all the points that are sand and it checks in an area around them. It gets the cells in the area around them, not on this script, it was right here. And it checks all those cells for each point, and if it's a water cell, then it sets it to shallow water, which is the lighter water, and then it loops through all the water that we didn't check, and it sets it to deep water, because that water isn't near any sand, so we can call it deep water. And with this, the map looks just perfect. Oh my gosh. This is so cool. But yeah, you can see I can adjust the radius, but it might like increase the like will decrease the performance. But I think this is fine. So yeah, you can just look at the outline it has, and it's perfect. It works for every seed that I've tried, and I'm quite proud of it. But yeah, this class for regions, because I don't know, I didn't need to make that class, but I did anyway. I'll probably change it later. Then we have the cells, which is nothing special. Updating the color of the cell, which just loops through the regions and applies the color. Map creation, just the same, but like you turn the noise map into cells. Get cells and radius is pretty cool. I had to search this stuff up because I didn't know what the heck I was doing. But yeah. And that's about it, I think. Nothing different really changed here. Well, I also like fixed the offset because apparently one based tables, you have to like, to get the actual middle, you have to add one to this and add one to this and divide by 2. It's weird, but it works. So yeah, that was interesting thing. Hope you liked it. See, I'll change the seed. Look at that. That's crazy. But yeah, this wasn't really a tutorial. It's just like a showcase of perlin noise, which I think is really cool. Hope you liked it. Bye bye.